Welcome to the lecture 19. This is unit 3, and this is the last lecture in unit 3. We're going to talk about the binomial distribution, and this is for statistics 2023. So basically the objective is that the binomial distribution allows us to find the exact probability of x successes in n trials of a binomial experiment, and I'm going to explain what a binomial experiment is. So many times the probability problems have only two outcomes, or we can reduce it to two outcomes. Flip of a coin, a child is born, or medical treatment, is it effective or ineffective? That allows us to get into the binomial experiment. So a binomial experiment is a probability experiment that satisfies the following four requirements. So these four requirements must be met in order for it to be a binomial experiment. The first one is that there must be a fixed number of trials. And then that each trial can only have two outcomes, or outcomes that can be reduced to two. And then the outcomes of each trial must be independent of one another. And then the probability of success has to remain the same for each trial. So if those four requirements are met, then we can have a binomial experiment. So a binomial experiment and its results give rise to the special probability distribution called the binomial distribution. Now, the outcomes of a binomial experiment and the corresponding probabilities of these outcomes are what we call the binomial distribution. And I have a distribution table which I'll show you in this lecture, and I'll also go ahead and post on Canvas. Now, in the binomial experiments, the outcomes are usually classified as success or failures. So, for example, the correct answer to multiple choice item, there's only one correct answer, that will be your success. So the notation for the binomial distribution are the following. P of S is the symbol for the probability of success. P of F is the symbol for the probability of failure. P is the numerical probability of a success, and then Q will be the numerical probability of failure. So P of S is equal to P, and then P of F will just be equal to 1 minus P, which is equal to Q. N will be the number of trials, and then X, or capital X, is the number of successes in n trials. Now, note that X is between 0 and n, so the number of successes has to be greater than 0, but it has to be less than or equal to the number of trials, and then X has to be equal to 1, 0, 1, 2, 3, all the way up to n. Now, the probability that a random variable X takes on a particular value in a binomial experiment is always the product of three basic factors. The first one is that the probability of exactly X successes is P raised to the X. Then the probability that a failure will occur on the remaining n minus X trials is Q raised to the n minus X. And then a number of ways that exactly X successes can occur in n trials. And that what happens is it gives rise to what we call the binomial coefficient. So the number of ways that exactly X successes can occur in a set of n trials is represented by NCR, or n choose R. And we've went over this in a few lectures ago. And this is always a positive integer. This is what we call the binomial coefficient. And so the binomial coefficient is found by using the following formula. And we've done this before. So n factorial divided by x factorial over n minus x factorial. But instead of x, we used R. So this then leads us to the binomial probability formula. So for a binomial experiment, P is the probability of success, Q is the probability of failure in a single trial. Then the probability P of X that there will be exactly X successes in n trials is given by P of X is equal to, and the first formula is just the combination formula, right? So n factorial divided by x factorial minus times n minus x factorials times P raised to the X times Q raised to the n minus X. So here's an example for tossing 5 coins, right? 5 coins to toss, find the probability of getting exactly 2 heads. So P of 2 would be 5 factorial, and that's the trials, divided by 2 factorial times 5 minus 2 factorial. Now the probability of success, or P, is 0.5, so we do 0.5 raised to the 2, well, that's our X, times 0.5 raised to the 5 minus 2, and that gives rise to the answer, which is 0.3125. So you get the formula, you know what X is, you know what N is, you just substitute that information into the formula, you know what P is and you know what Q is, and so you have everything you need to evaluate the probability of x, whatever x might be. In this case is 2. So this is a binomial experiment because there are a fixed number of trials, which is 5. There are only 2 outcomes, head or tails. The outcomes are independent, and then the probability of success, or P of S, is the same each time, which is 0.5, and it meets the 4 criteria. So now, consider an experiment that calls for drawing 5 cards, one at a time, with replacement from a well-shuffled deck of playing cards. The drawn card is identified as a spade or not a spade. It's returned to the deck is reshuffled, and then so on. So the random variable x is the number of spades that are gotten in 5 drawing. So what we're going to do is we're going to find the binomial probability function, and then we're going to use the binomial probability function to find P of x for each value of x. So the probability function is this one, and so we have 5 trials. The probability of success is 0.25 because we're looking for spades. There are 4 suits, so there's 1 out of 4. So probability of failure is 0.75. So that's where those values come from. And x would be, so what are the possible outcomes? So how many spades can I get every time I do one of these trials with 5 drawings? So what happens is that P of x, so x when it's 0, so the probability that I get 0 spades is 0.237. Probability I get 1 spade is 0.396, 2 spades is 0.264, 3 spades is 0.088, 4 is 0.015, and then getting 5 spades is a really low probability, which is 0.0009. And we can evaluate each one of these simply by replacing x with 0, and then we'll get the 0.237. With 1, we'll get the 0.396, and so on. So here's another example. A survey found that 30% of teenagers consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have a part-time job. So the probability that at least 3 is equal to the probability of 3 plus the probability of 4 plus the probability of 5. So then the probability of 3 using the binomial formula gives us 0.132. Again, it says 30%, so that means 70% don't have a job. Our x is 3. 5 is our number of trials. 5 minus 3 is 2, and that's how we get the 2 as the exponent for the 0.7. The probability of 4 is 0.028. As you notice, the probabilities remain the same. Number of trials remain the same. Probability of 5 is 0.002. And then we add those 3 probabilities together. So the probability that at least 3 teenagers have a part-time job is 0.162. Now, the next thing that we're going to do is we're going to use a table. And if we remember that previously we said, so the probability of getting 2 heads if I flip 5 coins is 0.312. So we're actually able to use a distribution table to get that information. So in this case, our probability is 0.5, trials is 5, and our x is 2. So let's go ahead and look at the table. So here's the table. And again, this is our n in this column, our r is in this column, and this is the probability p, and if you can see that right there. So we had a probability of 0.5. So 0.5, our trials were 5. So we're going to look at this row right here. So we're going to go to 0.5 and 5, and then we're looking for 2. So if we follow this along, if we see that the probability is 0.5, n is 5, r is 2, we notice that we actually get the probability, which is 0.312. All right, so let me get back to... So again, we're going to go ahead and do this example. We're going to go ahead and use the distribution table. So a report from the Secretary of Health and Human Services stated that 70% of single vehicle traffic fatalities that occur at night on weekends involve an intoxicated driver. If a sample of 15 single vehicle fatalities that occur at night on a weekend is selected, find the probability that exactly 12 involve a driver who is in fact intoxicated. So the information that we need in order to use the table is just n, the number of trials is 15, the probability is 0.7, and x is 12. Now we can use the formula, but using the tables is a little easier. So again, we're using n is 15, p is 0.7, and x is 12. So using the table, we have to look for n is 15. So here's the n is 15. So the next thing is we're looking for 0.7, which is this column over here, and then 12. So we're going to go across the 12 until we get to the 0.7, and we get 0.17. So the answer to the problem is about 17%. So let's go back here so we can see the problem. So if we choose randomly select 15 single vehicle fatalities that occurred at night on the weekend, the probability that exactly 12 of those would be an intoxicated driver is about 17% using the distribution table. Now, the mean and standard deviation for a theoretical binomial probability distribution can be found by using the following formulas. The mean is just n times p, which is the number of trials times the probability of success. The variance is just n times p times q, and the standard deviation is just a square root of n times p times q. So, coin is tossed 5 times. Let's find the mean, the variance, and the standard deviation of number of heads that will be obtained. So n equals 5, p is 1/2, q is 1/2. So that means that the mean is 2.5, which is 5 times 0.5. Now, the variance is 1.25, and the standard deviation is 1.12. So that's how you find the mean, the variance, and the standard deviation for a binomial experiment. So here's another example. The statistical bulletin published by the Metropolitan Life Insurance Company reported that 2% of all American births result in twins. If a random sample of 8,000 births is taken, find the mean, the variance, and the standard deviation of the number of births that will result in twins. So we have n is 8,000. The success is 0.02, so that's 160 births, with a variance of 156.8. Again, hold the information that we have as there. The way that we got q is just 1 minus p, and then the standard deviation will be 12.5. So for the sample, the average number of births that will result in twins is 160, with a variance of 156.8, and a standard deviation of 12.5 or 13 if we round. And that's the end of Lecture 19, Unit 3. Thank you.